the solar disk and magnify that to a much greater degree than I can.
Do you think
lesser?
Could we do that live? Could we try that? Because I want to. There's a part of the sun that I would like to show people. If you could do it, am I asking too much right now?
I can do this.
All right. So what I want you to do is come up in this view to the upper left-hand portion of where the moon is cutting into the sun, because just beyond that, on the limb of the sun, I think you can see a solar prominence, and I think that that would be cool in the context of this eclipse. Do you see what I'm talking about?
Yeah, let me just adjust my gamma here, and I can bring this up. And there's a few seconds of lag time here, but in a moment the disk will brighten, and you can tell me exactly which one you'd like to image here.
Okay.
So it should brighten any second.
And so what we're looking at, for those just joining us, this is from Matt's Prescott Observatory. This is a special telescope set up to look at the sun. We are looking live at the solar disk on the air, and what you're seeing, that cutout across the top limb of the sun, if you will, that right there that we're looking at, that we're showing on the cursor, that's the moon. Matt has already gone past his time of the maximum solar eclipse in Prescott, and now we're watching the moon starting to slide away. We're still seeing that full disk image, Matt. So if you can switch it,
I can switch it. It's going to take me. You will see the solar disk shift its position down the screen. So everyone will have to be a bit patient as I slew the telescope to a new position, so that I can image what you are asking. So let's.
All right. And while you're doing that, let me just tell everybody that SLU covers as many things as we can that happen in the sky, whether it be a partial solar eclipse like today, or Sunday's passage of the comet siding spring very close to the surface of Mars, or the total lunar eclipse, or the Orionid meteor shower, or just a plethora of things that go on in the night sky. This is the kind of thing that television networks are not going to cover, that just doesn't have the same kind of audience that it would need to put on network television, but that works perfectly for us. And we love having you here to see these. We feel that it is an honor to be able to bring a little bit of extra science to all of you that is not normally available in a way that you can see these things that is not normally available. And so that's what SLU is all about. And of course, as we mentioned from time to time, and there's that tight spot of the sun that we're looking at right now. And Matt is going to continue to adjust, I believe, the contrast so we can take a look at that prominence that is visible. There it is on the outer edge of the solar disk. That's great, Matt. That's fabulous. Tell everybody what it is that we're looking at right there.
Okay, so you're looking at the eastern limb of the sun. You can see it brightening now. I'm adjusting my exposure to a longer time and my gamma up to reveal the solar prominence on the disk. This is a feature that will be in a day to maybe 2-3 days. We'll be rotating into our view, so it's another active region that is about to be within our field of view in a few days, although I highly doubt it's going to compare with what is happening on the sun right now. This has been one of the most exciting last few days of looking at the sun that I've ever had. It's the biggest active region that has been on the sun this solar cycle. But yeah, what you're seeing right now is actually a pretty small flare there, a pretty small prominence.
Can you take a guess, some sort of dimensions, just ballpark figures, of how far off the solar surface that is?
I would guess the diameter, perhaps Earth-sized diameter. So the entire, diameter of our planet.
So for us, this is large, but basically in terms of using the sun as our reference point, it's not. And if you want to go back to that big sunspot region there in the center,
Sure.
that you were talking about, we can look at that as well. And we will show you more, by the way, of the moon sliding across the sun. This image that you're looking at, this time lapse, comes to us from the National Solar Observatory. You're looking at a couple of days worth, and you can see how that observatory is in Big Bear, California. How the eclipse is partial. The sun moved in across the disk. As it moves, these eclipses always take place with a westerly to easterly motion. So it came out of the west and slid across the sky. This is, in essence, what you're looking at, the moon's shadow across the earth, and the moon blocking to us our vision of the sun. But that is what it looks like in time lapse from the National Solar Observatory. You know, not only do we have Matt's observatory, but there are a number of solar observatories across the globe. Not only this one that we see in Big Bear, but also Solar Observatory in Hawaii. Actually, one not too far from our SLU Observatory in Tete in the Canary Islands. Also, not far from our SLU Observatory, there is a solar observatory, a major one in Chile, and all of them to look at what's going on the sun, our nearest star. Let's take a look at what Matt's working on right now on his screen, where we're looking with Matt's observatory at the solar disk. We're going to get to that in just a second here. And on that disk, you will see just below the center. Actually, you can also see it in this. There it is. Oh, that is fabulous, Matt. Tell me what here. The expression now on the internet is explain it like I'm in the 5th grade. So hit me. Explain what we're seeing like I'm in the 5th grade.
Okay, so we're seeing a highly magnified view of this huge monster active region on the solar disk right now. So the dark spots, the darkest spot there is called the umbra, and it's dark because that's exactly where these huge, and when I say huge, I'm talking about perhaps three of our planets would probably fit in that largest dark region there. And that dark region is being caused by a magnetic field line. It's exiting the sun there. It's being light to go out into space, but it's being pulled back by the oppositely charged region. One of these partner dark spots is pulling that magnetic field line back into the sun, and that's why there's sunspots are always in pairs. You're seeing these different oppositely charged polar regions interacting with each other, and in this case, on such a scale that this active region alone, this week has produced 27 C-class solar flares, and 8-class solar flares, and 2X, the most powerful solar flare possible, 2 X-class flares. And it's, as you can see, it's not even halfway across the sun yet.
Now, here on Earth, we have seasons where the weather changes, and every January, you might not have the same weather every January, but it'll be similar. The sun also sort of has seasons in that it has its solar cycle. Can you talk a little bit about that?
Sure, it does have a solar cycle. It's every 11 years, and we are, well, we don't actually know if we're at the absolute height of this solar cycle in terms of activity. I think most of us thought that we were past the maximum, and indeed we may be, but this week has certainly shown us that the sun is still quite active. So yes, every 11 years the sun becomes active in terms of number of sunspots moving across the disk, number of flares and CMEs, that type of thing, and another
coronal mass ejection.
Yes, coronal mass ejection, the most powerful type of energy release from the sun. And
Matt,
another.
can we switch back to the full disk view while you're talking, if that's okay?
Sure. In another 5 years years or so, it's expected that there won't be any sunspots, and we'll be at a quiet time.
Now, we've been looking at these for hundreds of years. I think that will surprise most people, but sunspots are one of the things that have been tracked forever, basically.
Yeah, that's right. They have been tracked for a very long time. If Bob were here, I'm sure he'd tell us the exact date. I wish I knew those numbers.
Yes.
But yeah, there was a an event called the Maunder Minimum, where some number of decades they didn't see a single sunspot. So we really, that's why it's great there are people like Lucy Green investigating this, because we really don't know that much about the sun, considering how in its proximity from us, you'd think that we would know a lot more about the sun than other things in the universe, but it continually is surprising researchers.
Matt, we've mentioned this a number of times today, but for those just joining us, can you tell everybody what that black line that looks like a thread that leads down from where the moon is now between us and the Earth into the solar disk? What is that specifically?
Yeah, that black line looks more to me like, since it's the month of Halloween, kind of like a scar, like you might see on Frankenstein's head. But yeah, it's a filament, and it's hovering above the photosphere. Filaments are traditionally highly unstable, and they erupt into CMEs quite frequently. And this filament that we're seeing appears black because it's slightly cooler than the surrounding region, but it's an extremely large filament. Again, this active region down in the southern hemisphere of the sun, just below the equatorial region, and this huge filament, the sun is unusually active this week, which is very exciting to us.
And is this image that we're looking at from your telescope, is this a visible light image, or are we looking at the sun in a way different than we mere humans usually see it?
Yeah, this particular image I'm using a hydrogen alpha filter. Actually the telescope I'm using is what we call a double stack telescope. So it uses hydrogen alpha wavelength, the one single wavelength of light that is especially, it reveals the texture, and it's a very high resolution image of the sun here, and with the double stack image, double stack telescope, what I mean is that we're using two of these filters in such a way that one of them can be pressure tuned to precisely tune that frequency into the imaging unit itself, and there's another tuner that's, we call it a tip tilt tuner, on the front of the telescope that precisely tunes this frequency of light. It's all about getting the exact perfect frequency right into the focuser and then into the imager.
You know, when you look at the sun like this, it does not look like a smooth object. You know, we sort of look at it in the sky and think, well, there's this smooth ball. First of all, what we're looking at, is there a surface to the sun, such as we would think of a surface, where you could, if you could take the heat, you could step onto the sun?
Boy, if there is a surface like that, it's far deep inside the sun. It certainly isn't anywhere near what we are looking at in this image now. Yeah, it would be much further deeper into the sun, and I honestly don't even know if we even know that for sure. I don't know how far their acoustical probes can penetrate down into the sun to see that kind of thing. That's really that's a question Lucy can probably answer better for us.
Well, S.E. Thompson has written us via Twitter using our hashtag #SLU_partial_solar and wants to know if that's an X-class or an M-class solar flare. How can you tell the difference? And I'll ask from dumb old me, what's the difference? And why do we care?
It's just the amount of energy, and I personally, with my equipment, I cannot tell the difference unless it's such a huge flare that it's obvious. But they're not obvious with my equipment. But the orbiting satellites that we have, that NASA has, can actually measure the energy output of these flares. And that's really the difference there between M class and X class. It's just the amount of energy. It can be from anything from radio waves to X-rays to gamma rays. And so the difference between an M class and an X class and why we should care, well, for one thing, M class solar flares produce fantastic auroras over the polar regions and spreading downwards and upwards. And the X-class solar flares is, I think most of us now realize, can cause, well, they can cause damage with our electronically dependent society.
In other words, they can send enough charged particles to Earth to stimulate electricity in transformers and things like that. Anywhere a wire is coiled, basically.
Yes, exactly. That, and also enough X-rays that aircraft along polar regions where when there's been an X-class coronal mass ejection that's due to hit Earth's atmosphere, those are always rerouted so as not to expose the passengers and pilots aboard to high-energy X-rays.
So I have a question here from Madri Srinivasan, who asks, is our current view already in the past, since light takes some light years to reach Earth? Well, the sun doesn't take light years to reach Earth. We're talking about light minutes to get this light year, right?
Yeah, that's exactly right. It's approximately 8 minutes. And again, it's, Bob would know it right down to the 10th of a second, I think. But yeah, it's approximately 8 minutes. So the image you're seeing, if you were actually right in front of the sun, is 8 minutes behind.
Now, and, when we look at the sun, we actually have a number of observatories that look at different parts of the sun or different features and take advantage of that time travel, if you will. We look at things visibly to start predicting things that are going to happen magnetically. Have I screwed that up, or have I basically gotten that right?
No, I think that's exactly right, Jeff. There are several orbiting observatories. You know, the Solar Dynamics Observatory, the Solar Heliospheric Observatory, Stereo A and B are on different angles from the sun than our line of sight, and those observatories and satellites can show us what is about to rotate into our field of view. And they measure some of these instruments can actually measure the magnetic field lines on the sun and these magnetic field regions. And that's our biggest predictor of solar activity in terms of oppositely charged regions. How large are they? How close in proximity to each other are they? So, in other words, how likely is it that they will interact and produce flares or coronal mass ejections?
Yeah, we have a clock running down on the screen, and that's the time until the eclipse ends at this observatory. As we've mentioned a number of times before, unlike a lunar eclipse, which happens at the same time everywhere, a solar eclipse is actually a sort of a movable feast. And this solar eclipse started its first visibility in Siberia, then came across the Bering Straits, into Alaska, through the Canadian Arctic, the Canadian Plains, down toward the Great Lakes states, and through the United States, not too far off, paralleling the Mississippi River as the visibility of the eclipse moved from the north to the south. Now, at the same time, the range of the eclipse was moving from the west to the east, and to make it just a little bit more confusing, at the same time, the sunset was moving from the east to the west. So at some places here in the United States, we had the solar eclipse. Well, at Boston, for instance, where I don't think it could have been seen because of weather anyway, but we had the first part of the eclipse take place basically at sunset, so that 0.9% of the sun was blocked, and then the sunset. Here on the West Coast, we're going to see the entirety of the solar eclipse, though never getting much more than about 40 or 45% here in California. Up in Washington and Oregon, they'll get more some places in Washington, as much as 60 or more percent. And they're at, I'm not sure of the exact number in Prescott, but I think you were somewhere north of 40% of the solar disk obscured by this eclipse where you were.
Yeah, yeah, that's correct, yeah.
And Lindsay wants to know if other stars experience filaments and coronal mass ejections just like we do from the sun.
Wow, that's a great question, and I can tell you we certainly don't have any reason to believe that they would not. Our star, there's nothing unusual about our star. I'm not aware of any imagers that have been able to actually image such a phenomenon happening on another star simply because of their distance from us. But I think that I think Lucy would agree with me. There's certainly no reason to believe that other stars don't go through similar events simply because we don't think that we're special. We don't think that our star is special or our solar system per se, really, and it's just a matter of statistics.
And there are billions of stars similar to our sun.
100 billion in this galaxy alone, and perhaps another 100 billion more galaxies. Our star is a main sequence star about well, it's a midlife star, kind of like me. And hopefully it won't go.
Now, explain that a little bit because some of our viewers today are fascinated by this, but really don't have a great deal of background. So let's give them a little something to take home. Why is this a mid-age star that we have?
It's a main sequence star. It's about halfway through its lifetime, so perhaps another 4.5 billion years before our star expends itself. So we are actually very lucky to be alive now in many ways. Like Bob was saying earlier, in another 100 million years, I think, which I know that sounds like a lot, but in
space time,
it's not.
right? It's very people. When we talk about stars and planets, you have to start thinking about space and time being in much larger increments than what we think of here on Earth. I mean, even that comet we talked about this past weekend, comet-siding spring, it's now heading out to the far reaches of the solar system. It's going to take about 1 million years to go as far as it's going to go. So a year or an hour or a decade is nothing in terms of the life of planets and stars.
That's right. That's right. I think the average human life, it's almost an insignificant, immeasurable amount of time when you compare it to cosmic time and how ancient our solar system, our planet, and indeed our galaxy is.
Matt, when you say that this star, our sun, is at midlife, if I would have been looking 3 billion years ago, would it have looked different to me?
It certainly would have. It would have been well, for one thing, it would have been much cooler. And I think that Lucy Green had spoke a little bit about that in terms of the problem of explaining the rise of life on Earth. And our star wouldn't have been even warm enough for liquid water. So it's really a conundrum for solar scientists and evolutionary biologists to explain this. I mean, I'm sure they will in time, but right now our understanding of how life arose in comparison to what we know about our own sun and its beginnings, it's incomplete.
And what we're looking at now, Matt, is the moon shadow on the Earth starting to make its final appearance as far as your observatory is concerned. This is very much a geography-dependent thing. This eclipse looks different everywhere that it's looked at, and the timing is slightly different everywhere that it's looked at.
That's right, and you talking about that reminded me of in one of Bob's books. It's called The Sun's Heartbeat. He talks about the history of scientific learning with eclipses and how developed countries would send these extravagant expeditions out to the far reaches of Earth to watch these eclipses and learn from them. And it's unbelievable what we've gone through as humans to try to learn about our origins and our own environment.
I think it's amazing to me what people like you know about the sun that no one knew 50 or 100 or 200 years ago, even though it's obviously the most dominant thing in our sky. And again, let me just point everybody who's looking to that upper left-hand portion, if you will, of the solar limb now as we watch the moon start to make its retreat and move away, move its shadow away from the Earth. What kind of things do we know, Matt, now that we have observatories like yours that we didn't know in the past?
Well, for one thing, we know, one of our listeners had tweeted in about all of the activity that's on the sun. You know, we could before there were telescopes and observatories like this. We didn't even know there were suns. Well, we didn't even know there were filaments and these huge active regions that go across the sun. We couldn't tell. We couldn't see the limb of the sun and see these coronal mass ejections that happen. And yeah, there's I couldn't even begin to tell you. Like, well, I am actually more amazed that these types of instruments are available to consumers. I mean, it's not, you know, almost everything I have was built in either California or Arizona. And it's just a matter of doing some research and deciding what kind of observing and imaging you want to do.
But you put this together with off-the-shelf hardware, basically.
Yeah, exactly. I mean, the optical tube assemblies are from companies in California and Arizona, as is the mount. And currently I'm building a solar telescope, a huge solar telescope with a colleague of mine. And we have high expectations for this.
And here we are in the last 20 seconds. It's very difficult now to even make out that there's any portion of the sun that's being eclipsed, but it will be gone in about 10 seconds. Matt, by the way, Alex has written in to tell us that the Kepler telescope has actually found that there are flares, as you postulated, that there are flares on other stars. So we do have some scientific evidence of that now.
Oh, that's great. Yeah, that's wonderful. Kepler is it's been in use searching for exoplanets, and in fact, I've actually used some of the Kepler data to reproduce exoplanet detection here at my own observatory.
All right. Well, listen, I think that we have seen it all this afternoon. So I can't begin to thank you enough, Matt, not only on behalf of me and the folks at SLU, who are always appreciative of the gracious use of your observatory, but I think, and I know that you will appreciate this as someone who loves the sky, who loves the physics behind the sun. We have introduced hundreds of thousands of people today to a little bit more science, to a little bit more in the way of physics, made it hopefully a lot of fun, and got people to see things that otherwise they would never be able to see. And you have to take a huge portion of the credit for that.
Oh, thank you, Jeff. I'm always happy to be a part of SLU. It's really a great community, a great organization, and yeah, like I said, I'm just happy to contribute.
All right. Well, thanks so much. That's Matt Francis. Matt is the proprietor of the Prescott Observatory in Prescott, Arizona. It is his solar observatory that has been bringing us like 99% of the pictures that we've seen this afternoon. We also want to thank the National Solar Observatory and also the Griffith Observatory in Los Angeles for allowing us to use their images this afternoon. Let me give you a couple of quick personal observations before we go away here. You know, everybody has a job. Everybody gets to work. there are few people who are as lucky as I am today who get to have a job where I get to bring you some really good, fun, scientific knowledge that you can take home. So if you're saying, Jeff, was this afternoon rewarding for you? The answer is yeah. I mean, how many people have this opportunity to be literally a do-gooder, as we have here at SLU this afternoon? So we thank you for joining us. Really briefly, I'm going to one more time touch on why SLU does these. We are the community observatory. We have 3 robotic telescopes located in the Canary Islands and in Chile. It's our members who point those telescopes every